will be given by Dr. Andrea Lausi. He is the scientific director of SESAME. Dr. Andrea Lausi, after graduating in physics at the University of Trieste, joined the surface science group of the University of Genova, focusing his activities on atom surface scattering phenomena. In 1996, he joined Electra, which is the Italian synchrotron source, where he initially participated in the design and construction of the first hard X-ray beamline. In the following years, Andrea Lausi presented the scientific case and managed the construction of two beamlines, MCX and Express. As head of the polar diffraction beamline, he developed instruments aimed to attract both the scientific and the industrial community. At Electra, he was involved in several international cooperation projects, and besides the responsibility of the Indo-Italian Beamline Express, he also represented Electra in several boards and occasions, from the Italian Crystallographic Association panel for instrumentation to the users meeting of the Mexican synchrotron project. He is also a member of the LAMP steering committee, and in April 2019 has been elected chair of the RICE working group, connecting the chief communication officers of the European Research Facilities Association. Since March 1st, 2020, Andrea Lausi is the scientific director of SESAME. He will talk of beats and phase 1 beamlines of SESAME. Andrea, it's for you now.
Thank you. Thank you very much for your nice introduction, and thank you very much for hosting me and us and SESAME and BEATS to this school, which should have happened in other ways. Actually, we should have had the pleasure of being there, but as we all know, we are forced to live online in these days, and so we do the best out of it in any case, and we try to go on. So my task here is to, after Axel has so beautifully explained the scene around beats, it is my turn to enlarge the scene to a wider floor, to explain where beats will be inserted, in which kind of environment will beats be constructed. And for that, I will recap also some of the concepts which are so effectively already mentioned in the talk of Dr. Hussein, which about what is synchrotron radiation and how it is produced, and for what purposes, and which wavelengths and energies. So let me go to this. Can you see my screen now? Okay, thank you. So this is SESAME, beautifully set in the olive trees landscape of Jordan, and this is a synchrotron radiation source. So if you go on Google, if you start from yourself and simply go on Google and try to discover what a synchrotron radiation source is, you are facing a wall of different informations of different kinds: technical, scientific, brilliance emittance, injectors, boosters, really too many concepts in one to digest rapidly. So a very, very basic primer could be that, first of all, it is not produced by synchrotrons. The names stick, but it should be more precisely known as radiation produced by charges moving at ultra-relativistic speed, and that's it. But it's obviously it is too long. So even if synchrotron is a horrible word, never ask physicists to make words. This shouldn't be our job. But still, you can see that as long as you have charges which are moving close to the speed of light, then you have, every time there is an acceleration involved, you have the emission of what is called synchrotron radiation. But synchrotron radiation, the name came from the fact that it was first observed in a tiny synchrotron at the end of the 40s. And then the name stuck simply, synchrotron radiation. No one of the facilities which are producing, not a single one of the facilities which are producing synchrotron radiation nowadays in the world are synchrotrons. They are storage rings or free electron lasers, but not synchrotrons. We use synchrotrons as a first stage to accelerate the normally electrons, all these charged particles at the end, we use normally electrons because they are light. You accelerate more easily light particles with respect to heavy particles. And the characteristics, going to a nutshell, there are two important characteristics which has made synchrotron radiation so successful in the scientific of today, which is the wide spectrum of the radiation. So you get out of one single machine, one single facility, you can get wavelengths which go from infrared up to hard X-rays in energy, or down to X-rays in wavelengths, which is an enormous because no other source is giving you so much in wide spectra, which means that you can do many different kinds of experiment out of it, because you can use radiation to know how the world is made in many different ways. And the other thing is brilliance. Brilliance is not simply the fact that we have really a lot of intensity, but this intensity comes also very in a very narrow beam. So brilliance is, you can use brilliance or brightness depending on which side of the pond you are, but essentially, if you look at the units, is the number of photons per unit of time, unit of angle, unit of source dimension, and bandwidth. So obviously, the higher this number, the better it is, mostly because we are not able to do easily the optics after it. So the more photons we start with, the better it is, because we will lose a lot of them during the process of taming the synchrotron radiation to the purpose at the end. So the more we have at the beginning, the better it is. In a nutshell, the idea is that this is what is normally called dipole radiation. An electric charge is an electric charge. It moves and while oscillating, emits a field in every direction. But in our case, this happens at nearly the speed of light, so 99.99999% of the speed of light, which means that we have a huge Doppler effect, ultra-relativistic Doppler effect, which squeezes incredibly much the wavelength of a factor gamma, actually in the direction of toward the observer, and in the other directions it goes so wide that the power emitted goes to zero. So at the end you finish up with a very narrow cone just in the forward direction, which is fantastic from the optical point of view. It allows you to put a lot of photons in a tiny point on the surface of your sample. Maybe among all the different magnetic structures which are used to make this dipole, the so-called most modern, the undulator, is the one which allows the easiest explanation of the overall effect. So a undulator is a set of magnets which are put in the path of an electron which otherwise would simply go straight. The electron sees this set of magnets coming into his directions while he is traveling at the speed of light as an electromagnetic wave impinging on him. And so it simply starts oscillating. It starts oscillating at a wavelength in his system of reference, which is Lorentz contracted because he's coming at, the electron is coming at the speed of light, or almost the speed of light. So it's the length of these poles are shrunk by a factor gamma, which in a synchrotron is around 2,000, 3,000, 4,000, 5,000. Then this electron in its reference frame does a dipole emission. So it's like a small antenna, no more than that. It's simply an antenna. And it emits radiations in all directions. But we are in the reference frame of the laboratory, so we see something which is Doppler shifted towards us. And this is a gain of a factor 1/2 gamma. So at the end, you have a wavelength which is much shorter of the physical length in the laboratory frame of the undulator, which is centimeters, and you go down to nanometers or even below, depending of which kind of machine you have. So what is the energy of the electrons? So what is your gamma, essentially? So in undulator radiation, what you have, as you can see here, you have these electrons passing through an electromagnetic wave, emitting electromagnetic radiation, and this is impinging on us in a very narrow cone and peaked at one energy, actually 1 energy plus all the harmonics, because there is interference between what is emitted at each and every pole. A bit more complicated to be described mathematically, but it can be done. What happens with just one, not all these wiggles, but just one wiggle? Then by the fact that you are viewing the electron for just a tiny moment, then the energy spectrum widens and you have the typical broad emission of a bending magnet. So these are the two main ingredients of how a modern synchrotron radiation source is built up. So you have some injection system which shoots electrons at the speed of light in a ring. In this ring, there are bending magnets which are there to maintain the orbits closed. And between bending magnets, with again, the fantasy which characterizes our physicists when we give names to things, inserted between magnets, there are the insertion devices, which wiggle somehow the electrons in their path and give rise to more intense and more, so you have the bending magnet radiation and the insertion device radiation at the end of these beamlines. This is extremely practical if you look at the shape of this thing, because with one single ring, you can feed at the same time many beamlines, many laboratories. So you just design the magnetic structure here and the optical structure there, which treats the photons which are coming out in a different way, and you have many different laboratories attached to the same machine, to the same ring. This ring actually, as I mentioned before, is called a storage ring. While the synchrotron is an accelerating machine, storage rings have only the scope to maintain the electrons in orbit for as long as possible, always at the same energy. And so they are not anymore synchrotrons. But okay, the name remained. So there might be a booster which is a synchrotron in the past story of these electrons, but this is not anymore a synchrotron. A synchrotron means the word comes from synchronos, same time, because if you have a synchrotron, using it as an accelerating machine, then the moment you raise the energy of the electrons, you synchronically have to increase the magnetic field of the bending magnets in order to maintain the same orbit. As simple as that. Synchrotron. why it's not moving? Oh, okay, sorry. Okay, so after we have produced the photons by moving electrons and shaking them in the storage ring, we still need something to reach our scope of having an experiment done. And this thing in the middle, the objective, it's like the objective of a photo camera, it's a beamline. It's a bit more complex to construct, but essentially it's something which tames the radiation, slits it down, focuses, unfocuses, puts it parallel, collimates, focuses again, selects one particular wavelength, and all this is called beamline. The important concept to remember if you want to be a beamline constructor, so someone who deals with the construction of beamline, is that unfortunately, the best that you can do is not to ruin the nice characteristics of synchrotron radiation, because the beam already comes very nicely out of it. It has a nice shape. It has so whatever you put in the middle will normally tend to degrade the quality of the beam. But you need it because you want, for example, to have a finer energy resolution than what is given from an undulator, which already has a peak. Or you are starting from a wiggler, like in the case of beads, and then you really want to select a particular wavelength, so you need a monochromator, and so on and so forth. So and you want to focus, you want to defocus, you might have many different needs with respect to the experiment that you have to, the class of experiments actually that you want to perform in that particular beam. So you start constructing a machine like SESAME or like in that picture Max 4 or whatever, and the ring stays in the middle, and outside it we will always find something like a donut-shaped experimental hole in which beamline after beamline you start to construct your laboratories. So if you apply yourself enough, this situation here of an empty floor becomes, in some years, a crowded floor with many experiments and pipes and tubes and chambers and experiments over there. And there are users coming from everywhere in the world to use these beamlines. At the end, what you have is, by, let's say, automatically, you have a cultural science center. This is a concept that was first introduced to me many years ago by David Atwood, and I always find it fascinating because it is really like this. The amount of different possible communities which can make use of a synchrotron is so huge, and the characteristic that they can meet also at the same time within the same walls, in the same experimental hall, and exchange ideas and problems and find new solutions. That is what really makes the synchrotron radiation facility an interesting place. It is not only the fact that it is a very good source of photons. It is not only the fact that it provides you with analytical instruments of high level, but it is also a place when you can get new ideas. This is very important to me, and this is an essential part of the mission of SESAME also. But it is in the DNA of every synchrotron radiation facility. So not only each synchrotron radiation facility is a community, but there are the communities of synchrotron radiation facilities. You see here a map of LEAPS, which is the League of Accelerator-Based Photon Sources in Europe. And SESAME, which is not in this picture because I didn't find the one it was produced, but SESAME is the first and for now only associate member of LEAPS in this moment. So you see by this impressive number the impact that synchrotron radiation had on the science in in Europe. A bit of a very quick history of SESAME. Just to get where we are now, SESAME started with some ideas of a few people. So this is a document which was undersigned in 1995 in Egypt, and brought up. So this was an Italian, Egyptian, Israeli meeting, and this brought to another meeting in Trieste, actually the place where I was born, and where the International Center of Theoretical Physics has its seat, and this brought to another meeting and another meeting and another meeting, until finally in 2003, without even having SESAME as an entity, Jordan decided to dedicate some land for SESAME. So you can build it here in Alan, in Jordan, on the 6th, there is a space missing, on the 6th of January 2003. Just a few months later, less than 1 year later, SESAME formally came into existence as an international facility with whose members are Pakistan, Iran, Palestine, Jordan, Israel, Cyprus, Turkey, and Egypt. And it started its long way to the construction of a real facility. The very first idea, which permeated the pioneering years and the first meetings, was to rebuild in Jordan the BESI 1, which was the old German synchrotron, which was substituted by BESI 2 in 1993, and was at that point looking for a new future, let's say. But fortunately, I must say, at the end prevailed. This was an important idea to start. And so, with a poetical justice, became the way we start the travel of the electrons in SESAME. Because it was clear that it wouldn't be possible to perform modern synchrotron radiation physics with a machine built in the 80s and disbanded at the beginning of the 90s. So the idea was, okay, let us build a competitive new third generation ring, which was done. But BESI 1 was still used as the injector, or refurbished and partly used as the injector of this new machine. So the seed of the idea remained. And okay, then came the years of the construction of the machine. You see here what happened along the years. In 2016, finally, the vacuum chambers started to be installed in SESAME. And there were contributions from Pakistan, who sent also technicians to help with the installation, because the staff was not enough numerous in SESAME, and Italy, who gave a contribution with the radio frequency cavities, which are the object which pump the energy at each and every turn to the electrons. And then we received also a solar power plant from EU that was funded to Jordan, and it's now extremely important to us because we are consuming quite a lot of current. It's a few megawatts, and SESAME is the only synchrotron which is powered by a solar plant, and this cuts by a factor 10 our electricity bills. So a non-negligible help here. And now, after all this construction, you see here the diagram of the current in the ring on a daily basis. So every day, current is injected in the ring. This is the amount of electrons which are running up during the hours. In 24 hours, we go to roughly 1/2 of what we had before. So the morning after, restart, re-inject, and again, and again, and again. And every day it's possible to measure something in these hours here while the electron beam is decaying. This is the shape of SESAME. It's a huge building with a ring in the middle, and so the travel of electrons starts here from this injector. It is a microtron, then goes to the booster. At each and every turn, this is a synchrotron. At each and every turn, they gain energy until they get to 2.5 gigaelectron volts. At 2.5 gigaelectron volts, they are injected in the main ring, where they remain at 2.5 gigaelectron volts for 1 day. And after, there is a new injection, and so on and so forth. And around it, we are constructing the various beamlines which are accepting the photons emitted, and we can use them to perform experiments. So what do we have now already? What is our suite of beamlines already available? The first one to enter into operation was the XF's XRF beamline, and I thank you, Dr. Hussain, for having already explained magnificently what the XF's is. So I can give that for granted. That it's a technique which allows you to know where the atoms are around an emitter. So you don't need crystallography, you just get the position of the atoms by exciting another atom inside the material. So these are the objects while they are put in the hatches, and this is the day of the first beam delivered to the beamline in the third quarter of 2017, and the fourth quarter. And then the first experiment that there is a known face, which Kirsi, who will speak just after me, and she was the first user of the first beamline of SESAME. And then this beamline being the first, obviously produced also the first paper, and paved the way for the future of SESAME. Since just some news of which we are particularly happy is that in December 2019, just a few months ago, a new fluorescence detector was developed in Italy and delivered to SESAME, and this is, I must say, definitely the best detector for fluorescence on the planet in this moment. This is the top edge in the class of fluorescence detectors. Nothing can detect photons so quickly and with such energy resolution until now. Then there is an infrared beamline. Infrared beamlines have a geometry which is completely different from the others. So you can reflect IR very easily. So you can go outside of a bending magnet, just put a mirror, go sideways, go up, cross the shielding wall of the ring, and come down and again and reach the experimental setup very easily. So this is a dramatic picture from above during the installation of the beamline. So this is the bending magnet, and this is the pipe which brings the photons out of the bending magnet. Here sits the first mirror, and from the first mirror you go straight here where the second mirror reflects the photons up. There is a third mirror, and the third mirror brings the photons out of the ring. And from out of the ring they reach here, and when they are again reflected downwards, sideways, and from sideways, this is here, this enters a connection box, and from the connection box you go to the microscope and into the spectrometer. This is also already operative and available for users. Material science, which is the name for the powder diffraction beamline of SESAME, is the first beamline which uses one of these wigglers or undulators. In this case, it is a wiggler, so it is The difference between wigglers and undulators is that wigglers are a multiplication of the bending magnets in a way, while undulators have also this interference effect. But wigglers are extremely powerful sources of hard X-rays for a low energy ring like SESAME. In the world, there are, let's say, two classes of synchrotrons, as I could have mentioned before, but there are machines around 4, 5, 6, or even more GeV, few of them, let's say one per continent, and these are the hard X-ray machines, and national machines which go between 2 and 3 gigaelectron volts, which can use undulators for producing soft X-rays and vacuum ultraviolet, and are with stronger magnets still can say a word in the hard X-rays world. So this is the optics of the beamline. It is a collimating mirror, a monochromator, and a focusing mirror. It is a very standard setting for such kind of beamlines. And this is the first beam just received on December 3rd. And then the construction was continuing until the beginning of Corona, and then stopped for a few months, and we are again starting in these days. So it will be available by the end of this year. HESEP, the Helmholtz SESAME soft X-ray beamline, this was already again mentioned by Dr. Sail in his speech before, and this will be the soft X-rays spectroscopy beamline of. This is a completely made in collaboration with Helmholtz Institute, and it has already been ordered. In September, we will have the first the final review of the project with the company who has won the tender for constructing the entire beamline. And after that, we'll start the construction, and we expect it to be here by the end of October next year, or maximum December next year. It will be a completely brand new beamline. The source will be a undulator, which will be a donation from BESSY 2, not BESSY 1, BESSY 2. So the new German ring in Berlin, and it has, like beads, a strong set of activities towards the community building. So Helmholtz launched a twinning project. Twinning project means that scientists from the members of SESAME can apply to have a beam time together with experienced users in Europe on a Helmholtz machine, which are a few of them. There is Daisy, Bessie, and Alba, and Anka, which has now another name actually, and Ket. Yeah. Okay. So there are several synchrotrons which can host with several groups users from member countries, and the call was open until 15 days ago for the first time. The first collection, so the first deadline was allowed to collect around 130 proposals, and now these will be. We are waiting now. We stopped the enrollment because we have to see what happens with this pandemic before starting. In this moment, most of the synchrotrons around the world are either closed or working only for corona-related research. And another activity which has been done by Helmholtz was the launching of a first HESEP soft X-rays workshop in Istanbul. And that was again a big success with 59 applicants from 36 institutions from the members. Again, this has not been possible due to the pandemic, but it will be firstly substituted by a webinar somewhere in September, October, still being organized, and then it will happen really in person again, hopefully in the next spring. HESEP by itself will come with a complete and up-to-date beamline with a fantastic source, good mirrors, everything top-notch, but a very simple experimental chamber, which will allow, in any case, to do studies, for example, on this kind of samples using the fluorescence effect. But, and it is not, so it is not by chance that the workshop was expected to be in Istanbul, because at the same time, in parallel, a consortium of Turkish institutions has obtained approximately 3.2 million euros from the Turkish government to construct a top-notch new experimental station for a branch line of HESEP. So this will be an instrument dedicated to photoemission spectroscopy. As mentioned before, it will be a spec instrument built up. You can build up these instruments more or less like Legos and adding more and different lead gas dosers, XPS, UPS, EAS, whatever ranges of electron energies you are looking for, and you can dose, prepare the sample in different ways. And this will be available again in around 2023 in SESAME, attached to the branch line of HESEP. Beats will be explored much better than just one slide as is here, but just to state the presence of beats among these and completes for now the suites of beamlines that will be available soon at SESAME. So 3 are already available, and other 2 will be available in a very near future. This is our guest house, which is waiting for users to come. It is 48 rooms and can host for longer periods with a canteen. It has meeting rooms. It can be both an educational center for workshops and hosting the users which are coming to use the beamlines of SESAME. This is just 30 meters from the entrance of the ring. So this is more or less taken. This picture is more or less taken from the roof just above my office. Proposals. Obviously, what we are doing in a synchrotron is to accept users which bring their proposals and do their experiments. We had already 3 calls for beam time. In the first one, 55 in total proposals were presented. In the second one, it doubled to 103, and now we are at 151 with 3 beamlines which can be addressed to. These proposals are then evaluated by an external panel of international experts. You see here all the names. And after this evaluation has taken, there are two colors because the green ones are the new ones, because when going from 100 to 151, I was just arrived and a rapid speech with the panelists explained me that they were not going just in 6 of them to evaluate 151 proposals. No way. After that, after the proposal is evaluated, the group has come and the Beamline has been used, then comes the publication of the results, which is the final goal of one particular proposal. So at the moment, I must say that the number of proposals, the number of successful proposals which have already led to a publication, considering that we are open since 2 years, is, in my opinion, extremely high. So already 8 papers after 2 years is, considering the time to analyze the data, write the article, and having it accepted in a journal. 8 papers in 2 years is quite a result already. But you see here the hidden part of the iceberg, which is the work done by the groups which come to make the measurements together with our Beamline scientists, because you see here, it's always Egypt, SESAME, France, Cyprus, SESAME, Iran, Turkey, SESAME, USA, and so on. So the SESAME staff is always, or almost always involved in the data analysis. It's part of their mission to allow the users to become more and more familiar with these techniques. And so they are preparing, and in many cases already submitted, many more papers which are in the pipeline. So there are 28 more papers in preparation in this moment. We are just going to open the gates for the next turn of proposals. And for the proposals which were, for those which will be selected out of the 151 of call 2. And we will most probably undergo a period of mail-in with the samples, but as soon as possible, we want to return to the normal user operation in which users come here and interact with our Beamline scientists and interact among them. Oh, sorry. So these are the papers, and so this is the community which is being built around SESAME, and I thank you very much for your attention.
Thank you very much, Andrea, for a very nice talk and updates about the SESAME. And it's a pleasure to see that SESAME is progressing very well. And we have a question for you from the participants. Anil Yusuf, are you there?
Yes, sir, I'm there.
Yeah.
Hello, sir. I'm Anil, and my background is in structural biology. And 2 years back, so while I was having the very same conference in Nathiagali Summer College, there at that time there was Giorgio Paolucci, and he briefed that in 2019 December there will be a beamline for macromolecule, but for a reason it has not been prepared for operation yet. My samples are of protein crystals, and I've been looking for SESAME to make macromolecule beamline established as soon as possible. And meanwhile, while I was talking to Giorgio Paolucci, while he was there, Dr. Christian Betzel was also there, and he said, right now we do not have our beamline operational, but Dr. Christian Betzel, he agreed to take me in his laboratory in Desi. And Dr. Paolucci, he promised me to arrange some funds from SESAME, which didn't work after, as he didn't respond. So what are the options for Pakistan if we are looking for collecting data for protein crystals, and if the SESAME is not operational for macromolecule crystals, where are we headed to? through SESAME, and what are the options for the scientist? Thank you.
Yes, so there are it is a twofold question. Thank you very much. And so first thing, the macromolecular crystallography beamline is in the plans of SESAME, but was abandoned during 2018 for now, and put aside because lack of funding. So all our funding were already used for the beamlines which I have described, and nothing was left at that point for a macromolecular crystallography beamline, which unfortunately is an extremely expensive beamline due to the need of a up-to-date detector. So you cannot, nowadays, you cannot build a beamline of that kind if you do not aim for the best beamline of that kind, or for the best that you can make. That means you need, in any case, robotics to change the samples, and you need a fast detector. Otherwise, you are not competitive. You are not attractive with respect to all the others beamlines. And so we will be looking for funding for sure for that. But I thought that would have been one of my priorities when I arrived here on the 1st of March, to go around between the members and Europe and the non-members in order to find this nucleate and reinforce this beamline in particular. But then what I experienced instead was lockdown and curfew. So I'm still waiting to start that part of the job. As for instead the access to other beamlines in Europe for macromolecular crystallography, there are many different plans that can be used either through SESAME and outside of SESAME in order to access these beamlines. And if you drop me an email at SESAME, we can discuss about it in details. But essentially, Electra has programs. Calypso Plus has programs for all European synchrotrons. SESAME has programs for the community of the members to support visits. So there are many different possibilities. Obviously, each of them is related to the, let's say, evaluation of some scientific panel, but that is normally not the problem. So I mean, good proposals are evaluated well. Yeah.
Okay. Thanks, Andrea, for elaborative reply. There is another question from Intikhab Ulfat from Karachi.
Hello, can you hear me all?
Yes, yes, please.
Thank you, and this was such a nice talk. I have a few administrative and technical questions actually, especially from Team Beats. Number one is, what is the plan for asking beam time applications for Beats? Secondly, the prerequisite sample preparation facility, what you plan to provide? Three, data handling, of course, in case of archaeological samples is a very important issue. And especially when it comes to preservation of samples and artifacts, I mean, how to handle these kind of issues. And as a director, as a scientific director, what about the beam time application simultaneously for instance, XRF and XRD? Being in Pakistan, you know, we would like to have a time such as that could go on for 2 weeks so that we can use all our samples. I'm really sorry to ask so many questions, but I'm a little excited as I have been a user at MaxLab, and I'm now very excited to use SESAME.
Thank you.
you
No,
very much.
absolutely. Thank you very much. Thank you for the questions. About let's start from the last one. There will be, as usual, an evaluating panel. So if more than one proposal is passed by the panel, we, like everywhere, we will try to cluster them in such a way that in just one sweep, one can go from one beamline to the other and do all the measurements one after the other. But remember, it will be very demanding on you, because one thing is to come and stay awake for 3 days continuously in front of the beamline. Another is staying awake for 14 days in front of 4 different beamlines. I mean, it can be done, but you will also have to coach a substantial amount of colleagues in order to survive this thing. But I didn't mention, but normally synchrotron radiation facilities are open 7 days a week, 24 hours a day, except for small interventions in the machine or other shutdowns due to programmed updates. So, and obviously the local staff can help, but cannot, they cannot work 7 hours, 45 hours a day. It's 7 days a week. So the nights are mostly on the shoulders of the users. So this is what makes the things also so interesting, that you learn how to use the beamline actually, and to analyze data and everything. It is not an analytical facility to which you send a sample normally. It will be for a while, but we hope to return to normal operation as soon as possible. Then about the sample preparation is, again, like for protein diffraction, one of the things that must be put in place as soon as possible, as soon as funding are available. It's simply a matter of finding the way of funding the initiatives. It is clear that a sample preparation laboratory is indeed very much needed by SESAME. It is not yet in place. And again, it will be part of my job to find out a way to have it, to manifest itself.
Yes, thank you very much. I understand all the things. Thank you.
Yeah,
thank you.
I mean, it's with an infinite budget, everything is possible. Hiring hundreds of people and preparing all kinds of laboratories in rapid times. But without that, it becomes a bit difficult. But believe me, we are very committed to do all this.
Yeah, I understand, because in the papers that you showed from Turkey, 6 papers, I am the author in the 2 of these papers actually. So I have been, I'm in the part already. Thank you very much.
Thank you.
Okay, thanks Andrea for a nice talk. Thank you very much.
Thank you.